lecture in which we continue a discussion on small signal amplifiers, and we will start with the effect of CE, that is the bypass capacitor. And as I said, engineers do not like to mix many things up, so for this discussion we assume that CC1, in considering the effect of CE, we assume that CC1 and CC2 both tend to infinity, that is both act as short circuits. It is only CE that is effective in controlling the low frequency gain. Now if I do that then my equivalent circuit becomes Vs, Rs, CC1 is taken as a short circuit and therefore I have R pi, and for a change let us use, instead of capital V, let us use the base current. The RMS value shall be represented by I sub capital B. That is the reason why I am using the current here instead of the voltage. This then in the collector circuit, collector to emitter, this is the emitter. I am not connecting it to the other end of Vs because I want to consider the effect of Re and Ce in parallel. This current generator is beta IB, and this goes to CC2 is also a short circuit, and therefore RC and RL, they come in parallel, and therefore they go to ground through a resistance R0. From E we shall have a parallel combination of Re and Ce. It is the effect of Ce that we wish to consider. We have already assumed that CC1 and CC2 go to infinity. Now the reason why I used currents here is now obvious. The current that flows here obviously is beta plus 1 I sub B, alright, beta plus 1 I sub B, and therefore the the drop, that is VE, no, I should use something else. Have I used the symbol correctly? No, I am trying to find the root mean squared value, small e, okay. V small e, therefore let us find this out. V small e equal to the current beta plus 1 IB multiplied by the impedance of Re and Ce in parallel, which means that 1 over the sum of admittances, that is 1 over Re plus j omega Ce. Is that okay? I could have written down the impedance directly, Re divided by j omega Ce Re plus 1, but I am doing it in steps. It is impedance is 1 by admittance, two elements are in parallel and therefore admittances add. For the resistance the admittance is 1 by Re, for the capacitance it is j omega Ce. This I can write as I sub B multiplied by, now I divide both numerator and denominator by beta plus 1. Then I get 1 over beta plus 1 Re, alright, plus j omega Ce divided by beta plus 1. Is that okay? Is that clear? Now if I write the KVL equation in the base circuit, then Vs would be IB times Rs plus IB times R pi plus VE. If I can write VE as the product of IB and an impedance, then obviously I can decouple the input and the output circuit. Is that clear? No. Well, my KVL is Vs equal to Rs plus R pi times I sub B plus VE. and VE I have expressed as I sub B multiplied by an impedance, let us say ZE. I have done that in this simplification. I write this as IB times ZE, where ZE is this quantity 1 by this whole thing, alright, and therefore my equivalent circuit as far as the input is concerned is simply a series combination of RS, R pi and ZE. What is ZE? Obviously ZE is a parallel combination of a resistance which is equal to beta plus 1 RE, not simply RE, and a capacitance whose value is CE divided by beta plus 1, alright, and therefore my input circuit effectively becomes like this Vs, Rs, R pi, and then I have a parallel combination of resistance beta plus 1 Re and a capacitance Ce divided by beta plus 1, alright, and this current is I sub B. You see, the advantage is that I have decoupled the output circuit. Now what will be the effective output circuit? Just let us look at that. Is this point clear? That I have allowed a current IB to flow through this. So what I have done is I have jacked up the resistance by beta plus 1, I have reduced the capacitance by beta plus 1, and this is an exact equivalence. I have not made no approximation, alright. Now let us look at the output circuit. Have I really decoupled? Interestingly enough, you notice that in the output circuit there is a current generator beta IB in series with a resistance R0 and this parallel combination of RE and CE. Now what would be the voltage across R0? It would be simply minus beta IB R0, and therefore this is independent of what I connect here. Why does this happen? Because a constant current generator delivers a current irrespective of what happens to the external world. What you connect here, the current generator simply ignores. It defies. You can connect anything, I shall still send a current beta IB. And therefore as far as the output circuit is concerned, we can safely ignore REC. There is no need for that. Is this point clear? Okay, and therefore my output circuit simply becomes beta IB, I am ignoring REC, and simply R0. This will be my V0. It turns out that in practice the impedance of this, that is beta plus 1 Re, is usually much greater than the impedance of the capacitor, that is beta plus 1 divided by omega CE. Is the point clear? CE is usually chosen large such that the impedance of the capacitor is much less than the impedance of the resistance, which means that safely you can ignore this part of the circuit. Is this point clear? If I have two impedances in parallel, one of them is very large compared to the other, then the effective impedance is that of the smaller one, and therefore the equivalent circuit simply becomes this, from which you can now calculate the gain, that is V0 by Vs. Now obviously V0 is equal to minus beta R0 times IB, alright. From the output circuit beta IB flows like this, and what is IB? IB is equal to Vs divided by Rs plus R pi plus 1 over j omega CE, while bring beta plus 1 here, alright. Now if I combine these two, then obviously I can get an expression for the gain, that is V0 by Vs, and you can see that V0 by Vs, simple algebra, is minus beta R0 divided by Rs plus R pi plus beta plus 1 divided by j omega Ce, alright, which I can write as, I have just combined those two terms. I can write this as minus beta R0 divided by Rs plus R pi, which precisely is what? The mid-band gain A0, 1 divided by 1 plus omega L divided by j omega. Okay, I take Rs plus R pi common, then what is omega L? Beta plus 1 divided by Ce Rs plus R pi. Can you see why I call this omega L, the low frequency 3 dB point? Because it was by design. I assumed Cc1 and Cc2 to go to infinity. So Ce now determines the low frequency 3 dB point, or the low frequency cutoff point, alright. And this is A0, and therefore the low frequency gain now, Al omega divided by A0, alright, the normalized gain is simply equal to 1 divided by 1 minus j omega L divided by omega. Alright, one capacitance Ce now determines the low frequency 3 dB point, provided Cc1 and Cc2 have been chosen sufficiently high. Okay, it is sometimes convenient to determine the low frequency 3 dB point by Ce rather than either Cc1 or Cc2. Let us illustrate this with the help of an example. Suppose we have a transistor amplifier in which Rs is 2K, let Re be 1K, alright, this is very practical values. Ce has been chosen arbitrarily as 50 microfarad, alright. R1 and R2 are very large, that is Rb is much larger than R pi. Well, this we had assumed right at the beginning. R pi is given as 1.5 K and beta is given as 50. R pi and beta are given, so you can find out Gm, you can find out I sub C if you require to calculate R1 and R2. And the question is, estimate FL, what is the low frequency 3 dB point, and if Rc is equal to 5K, RL equal to 10K, then what should be Cc1 and Cc2? You understand the question? This is what is given, this is the data that is given. What is the low frequency 3 dB point? In other words, you are being asked to design a circuit in which the low frequency 3 dB point is predetermined by Ce, and then you are asked what should be your values of Cc1 and Cc2. Okay, the design proceeds like this. Since Ce determines the low frequency 3 dB point, therefore you can calculate FL as equal to beta plus 1 divided by 2 pi Ce Rs plus R pi, alright, and you substitute the values of beta 51, 2 pi times 50 times 10 to the minus 6, Rs is 2K and R pi is 1K, so 2 plus 1 times 10 to the 3, and this calculates out to approximately 45 hertz. 45 hertz. If you want 5 hertz, then you have to use what value of capacity? What? 450 microfarad, yes. Even 1000 microfarad is available. These are electrolytic capacitors, all right, and therefore if it is a stereo amplifier and this is what is given to you, you say your design is bad, I will increase the capacitor 9 times, well then I will get 5 Hz as the cutoff, all right, and these things should be very obvious to you, where to change and what to change, all right. FL is 45 Hz. Now beta plus 1 RE, if you recall, we had ignored compared to the impedance of the capacitor. Okay, beta plus 1 RE is how much here? 51 times RE is 1K, so 51K. And beta plus 1 divided by omega L CE is 51 divided by 2 pi times 45 times 50 into 10 to the minus 6. All right, this calculates out to approximately 3.3 K. And you see why we ignored beta plus 1 RE. It's about 16 times the impedance of the capacitor, and therefore that approximation is valid in practice. The next point is how to choose CC1 and CC2. If we recall what we did, the design philosophy is like this. With this omega L, you calculate the required value of CC1 and CC2 and call them CC1 prime and CC2 prime. Then in the actual circuit you use at least 5 times this value. For example, here in this example, CC1 prime would be 1 over omega L, that is 2 pi times 45, yes, RS plus R pi, RS is 2K and R pi is 1.5K, and this calculates out approximately to 1 microfarad. Approximately 1 microfarad, 3.5, 7 times 5, yeah, it's approximately 1 microfarad. Similarly, CC2 prime will calculate like this, 2 pi times 45, then RC plus RL, they are both given, so it is 15K, all right, and this calculates out to approximately 0.22 microfarad. So in this circuit what you use is 5 times this, 5 microfarad, you don't get 5, you get 4.7, all right, or 6.8, or use 6.8, use 10 microfarad, why not, even that is available, incremental cost, maybe a rupee more, which is worth it, okay. And CC2 you shall use at least 5 times this, well 1 microfarad is a good figure, okay, 1 microfarad or slightly higher, 2 microfarad is also available, well, use 2 microfarad.
So but we said that they will use the larger of the two as such and the second one
larger of the two. No, here the situation is slightly different. Here the situation is 3 capacitors. We have already chosen CE, that is the largest value, 50 microfarad. Larger of the two is when CE is assumed to be infinity. Let me recollect what I said. If your choice is to determine omega L, can I have your attention? If your choice is to determine omega L by either CC1 or CC2, assuming CE to go to infinity, CE is 1000 microfarad, you have already done that. Then you calculate from the specified omega L, you calculate CC1 and CC2, have the larger of the two as the value that is calculated, the smaller one you multiply 5 times. That is a different situation. In our situation we are determining omega L by CE and trying to find out what should be our values of CC1 and CC2. Whatever you calculate Cc1 and Cc2 from the given omega L, you multiply 5 times. Then it will make sure that Ce omega L determined by C is the largest of the 3. And so this will determine the low frequency 3 dB cutoff point. Now one can be fussy and one can say, why don't I optimize? Why don't I optimize by using the minimum possible capacitances? That is, I use all the 3 together and then try to find out by solving a 6th order algebraic equation numerically what omega L shall be. It's not worth it, alright, because capacitors, large electrolytic capacitors are available plenty. If space is a premium, if space is a problem, you might have to do that. But then if space is a premium, what you do is you use very small power supply also. For example, a circuit to be put in space in a satellite. Well, you depend on the solar battery. The power supply is small. So you use low resistances. And if you use low resistances, the capacitors have to be sufficiently high. But the current level is small and therefore you use semiconductor capacitors. You don't use electrolyte. These are facts of life, compromises of life that one has to make. Alright. Now so far so good about mid-band and low frequency. What do we do at high frequency? How do you determine at high frequency, as you remember, omega H, and this is A0. How do you determine the high frequency 3 dB cutoff? At high frequencies, the Cc1, Cc2 and Ce, all of them are shorts. What is effective is the internal capacitances of the transistor, that is C pi and C mu. Now let us see how C pi and C mu affect the circuit. The equivalent circuit, if you draw, it would be Vs, the series resistance Rs inevitably present. We ignore Rb as we have done earlier, so we shall have R pi. Now Ce is short and therefore this will be grounded, R pi, and in addition we must have the capacitor C pi. This voltage is V, this voltage is V, and then we have between C pi, between this end and the collector, we have the capacitor C mu, the current generator is GMV, and then we have Cc2 is short, therefore Rc and RL are in parallel, and so R0, and this is V0. Now since you have taken a course from SCDR, I take it that you are very good in circuit analysis. Now you can make nodal analysis, you can make loop analysis and so on, but try to do this for this simple circuit. In terms of symbols, life becomes miserable because there is a controlled current source here. And so as electrical engineers, in common with other engineers, we try to simplify matters. And this is where a gentleman by the name Miller, C.J. Miller, M-I-L-L-E-R, contributed very substantially. Miller was a practicing engineer and he found this kind of an analysis very troublesome. He was not good at loop analysis, node analysis and so he said, I will simplify the matter. Let us look at Miller's philosophy a little carefully, then we shall go back to this circuit. Please try to follow this carefully. Suppose we have an amplifier or a 2-port. Suppose we have a 2-port in which the output voltage V2 is equal to A times V1. Alright. Suppose we have a 2-port in which the output voltage V2 is equal to A times V1, and suppose we connect an impedance Z here. That is, we have a bridging impedance, bridge. It bridges the input port to the output port. All right. What is the current through this I? What is the current through this? Obviously, I shall be equal to V1 minus V2 divided by Z. And since V2 is A times V1, we get V1 times 1 minus A divided by Z. All right. Look at the simplicity of the concept. Then I write this as V1 divided by Z by 1 minus A. What does it mean? It means that as far as the input port is concerned, the effect of the bridging impedance is simply that you get in shunt an impedance which is not Z but Z by 1 minus A. Is that clear? No? You see, I want to convert this circuit into one in which the bridging impedance is not there. And the clue is, why did Miller think so? Miller found this very disturbing, this C mu. It's bridging the input and the output. You see, previously in our mid band as well as low frequency, C mu was not there. And analysis was absolutely by inspection, common sense, nothing else. No node analysis, no loop analysis, nothing. You just looked at the circuit and wrote down the expression. With this, you cannot do this. So he said, can I replace this bridging impedance by an equivalent impedance at the input and an equivalent impedance at the output? This is what he argued. And so what he said is, what does this bridging impedance do? Well, it extracts an additional current I. If I can account for this current, then obviously the bridging impedance can be ignored as far as the input is concerned. So at the input, what we shall have is, since this current is only now proportional to V1, what I will do is, between this point and this point, I will connect Z by 1 minus A. All right. Similarly, let us look at the output. What does the output do? Output, there is a current I, and this current I, well, let us call this output as, this current as I prime. I prime. Can you tell me what is I prime? V2 divided by what? Pardon me? Z divided by 1 minus 1 by A. Isn't that right? Okay. And therefore, at the output, the bridging impedance acts as if the impedance is divided by a quantity 1 by 1 minus A. Z divided by 1 yeah, that is perfectly all right. Okay. So equivalently then, I can replace this circuit which had a bridging impedance by one which does not have a bridging impedance, and they are exact equivalents. I have made no simplification, no approximation. What I have here is an impedance Z by 1 minus A, and what I have here is Z divided by 1 minus 1 over A. All right. The question is, what is A? For this transistor circuit, can we for a moment go back to the transistor circuit? Let us look at the transistor circuit once more. What is A? You see, A is V0 divided by V. And this is where Miller said, let us play a little smart. In calculating A, let us ignore C mu. If I do that, then what is A? This is V and this is GMV. GMV minus GMV R0 is the output voltage. Output voltage divided by input voltage, that is V. So the gain is simply minus GM minus GM R0. This is approximate. All right. So, yes, please repeat. Miller said, in calculating A, we required this value of A, that is V2 equal to A times V1. in calculating the value of A for the transistor circuit, let us ignore C mu. Alright. If I do that, then the output divided by input V0 by V is simply minus Gm times R0. This is an approximate picture. Alright. So, capital A for our case capital A approximately equal to minus Gm R0. You understand this approximation? In calculating capital A, we have ignored C mu. Alright. What is Z in our case? The bridging impedance is 1 over j omega C mu. Alright. This is the bridging impedance, and therefore at the input Z divided by 1 minus A is equal to 1 over j omega C mu times 1 plus Gm R naught. Is the point clear? Our effective input impedance, reflected input impedance, is 1 over j omega C mu 1 plus Gm R naught. And you see what happens. C mu is a small capacitor of the order of 3 puffs, and C mu is now multiplied by 1 plus the gain of the circuit. If the gain is 99 and C mu is 3 puffs, equivalently it is reflected at the input across C pi as 300 puffs. Is the point clear? Even a small capacitor can cause devastation in the input circuit, because it can swamp C pi. C pi is only of the order of 100 puffs, and if the gain is 1000, well, 3000 puffs, C pi can be safely ignored. This is what the effect of C mu is. Even though it is a very small capacitor, it can reflect at the input as a large capacitor. Now, what happens to the output circuit? At the output circuit, it is reflected as Z divided by 1 minus 1 by A, which means it is 1 over j omega C mu times 1 plus 1 over Gm R naught. And if Gm R naught is of the order of 100, then safely this can be ignored. Safely this term can be ignored. Therefore, at the output, C mu remains as C mu. Is this point clear? And this effect, or this method of calculation, this effect is known as the Miller effect. That is, a small capacitor, a small impedance is reflected, a small capacitor is reflected as a large capacitor. This is called the Miller effect, and the whole theorem is known as Miller's theorem. If I take account of Miller's theorem, then you see my equivalent circuit now becomes Vs Rs R pi C pi, and then, pardon me?
You said we can ignore C pi.
No, let us keep it for the time being. It will depend on the value of the gain. C pi, and then the Miller reflected capacitor, which we shall call as Cm. Cm is C mu multiplied by 1 plus Gm R naught. Okay, there are two capacitances now, and the two together we shall represent as Ct, the total input capacitance. Ct is C pi plus Cm, and the voltage across this is V. Since we have taken account of C mu, the bridging capacitance, our input circuit is decoupled from the output circuit. So, we have GMV, now we go happily, GMV, but you must reflect Z by 1 minus 1 by A, that is C mu here. There is a C mu, and in parallel with R0. Now, R0 as you know, is of the order of a few Ks, okay, maybe parallel combination of 4K and 4K, it makes only 2K, whereas C mu is a very small capacitor, 3 puffs. So the impedance of C mu shall in all probability be very large compared to R naught, and this C mu can be ignored. These are practical simplifications. A large impedance shunting a small impedance has no effect, and so we can ignore this, and we can combine these two into a single capacitor CT, which gives me the equivalent circuit. The following equivalent circuit: we have Vs ignoring C mu. Okay, I said that R naught is of the order of a few Ks. Let's say it is 2K. C mu is a 3-puff capacitor, 3-puff. Alright, let's see the end of the audio band, 20 kilohertz. So at 20 kilohertz, the impedance of 3 puffs is 20 times 10 to the 3, 2 pi times this, multiplied by 3 times 10 to the minus 12. And if you calculate this will be very large compared to 2K. It would be of the order of megs, and therefore the effect of C mu can be ignored. A large impedance shunting a small impedance has no effect, and therefore we ignored that. The equivalent circuit now becomes Vs, Rs, R pi and Ct. R pi and Ct, this voltage is V, and in the output circuit we have GMV multiplied by, not multiplied, in shunt with R0, and this is the voltage V0. To calculate the gain V0 by Vs, you notice that V0 is minus GM R0 multiplied by V. Alright. Now look at the simplification that comes into effect. Minus GM R0, V is, let's call this impedance as ZT, the impedance of R pi and Ct in parallel, let's call it ZT. Then it would be ZT divided by Rs plus ZT multiplied by Vs. So we take V0 by Vs, the normalized, the gain, and we call this A, gain, as a function of frequency. At high frequencies, AH omega is given by minus GM R0 divided by ZT plus Rs plus ZT. Okay, let's write this expression. What is ZT? ZT you can easily show, this is R pi divided by 1 plus J omega R pi Ct. If I substitute this, let us see what happens. AH omega becomes equal to minus GM R naught R pi divided by 1 plus J omega R pi Ct divided by Rs plus R pi divided by 1 plus J omega R pi Ct. I have simply substituted for Zt. Alright. Now I multiply both numerator and denominator by 1 plus J omega R pi Ct. And you also notice that in the numerator I have Gm and R pi. So I can write minus beta R naught divided by Rs. Rs multiplies this. Rs and R pi is left alone. Rs plus R pi plus J omega R pi Ct Rs. Is that okay? And now I take this out. You see, my purpose is to bring the mid-band gain in some manner or other. Mid-band gain is minus beta R0 divided by Rs plus R pi, and this I can write as 1 plus J omega by omega h, where omega h is defined as what? 1 by r pi CTRS. No, not quite. Into Rs plus r pi. And don't you see that this is simply 1 over Ct r pi parallel Rs. This therefore is the high frequency 3 dB point. At omega equal to omega h, the gain becomes 1 by root 2 times the value at midband. That is my normalized gain. My normalized gain now, AH omega divided by A0 becomes simply equal to 1 plus j omega by omega h. Is that okay? There are no other capacitors determining the omega h. Why not? We had started with 2 capacitors. How come we are left with only 1? Because we ignored no. CC1 and CC2 and C have no business to show their faces at high frequency. C mu at the output circuit, we ignored its effect. Suppose we included the effect, what would have happened? Omega h now from it is Ct r pi parallel Rs. If we had included C mu, we would have got some omega mu which is equal to 1 over C mu times time constant would have been C mu times R0, and this omega mu would have been much greater than omega h, because C mu is a very small quantity. Is the point clear? Now between 2 values of omega h and omega mu, the lower one shall determine the high frequency 3 dB point. Is this point clear? In the low frequency case, you had omega 1 and omega 1 and the higher one was determining omega L, because if this is omega 1 and this is omega 1, it is this which is close to 1 by root 2 point. On the other hand, at high frequencies, it is the smaller one that shall determine, and therefore this is the high frequency 3 dB cutoff point. And we could determine this because Miller was there. Well, it's not that we cannot determine this. We can do this numerically. If the values are given, we will solve an equation, an algebraic equation, and solve it. But you see, the analysis has become almost by inspection now. In the remaining few minutes, I shall introduce 2 terms and then let you go and have this concept simmered. 2 terms. A transistor manufacturer usually does not specify C pi. He specifies a quantity known as F beta or a quantity known as Ft. While the names of these are beta cutoff frequency, and this is called the transition frequency. And the definition comes like this. Suppose you drive a transistor with a current source IB, all right, and you find out the short circuit output current. You take a common emitter transistor, drive it with a signal source IB, current generator, short the output and find out the current. Well, in terms of the equivalent circuit, you see in the base you have R pi, C pi, then you have C mu, then you have GMV, this is V, and as I said, you short circuit the collector, then this current would be I sub C, the output current, the collector current, alright, and the ratio of I sub C to I sub B would be the current gain or current amplification factor, and to indicate that this is done under short circuit conditions, we say this is the short circuit current amplification factor, alright. If I calculate this, you see obviously I sub C is equal to GMV, isn't that right? I sub C is equal to GMV, alright. I sub C equal to GMV. No? Pardon me? I sub C is not equal to GMV? It's a short circuit, and therefore the current generator, why should it send the current through impedances? It finds a short circuit, so it sends all its current here. No? There is no approximation here, this is exact. The current generator, it also looks for the shortest possible path. Like every system in the world goes to its lowest potential energy. Why should the current generator be obliged to send the current through C mu? No, it doesn't. It sends all its currents through the short circuit. So I sub C is GMV. But what is V? You see this point is virtually grounded. That means if I look at the input circuit, it is as if we have a capacitor C pi plus C mu, and therefore V is I sub B multiplied by R pi divided by 1 plus j omega R pi C pi plus C mu. Alright? Is the point clear? I sub B, this current generator, flows through this impedance, and this impedance consists of R pi parallel C pi parallel C mu. The current generator does not come into effect. Alright? This is what I have written. And you also know that C mu is only of the order of 3 puffs and C pi is of the order of 100. So you ignore C mu. Alright? So you can write now I sub C by I sub B, okay, short circuit output current divided by the input current, base current, and this quantity is represented as beta, but beta as a function of frequency, beta as a function of frequency, beta omega. And you can see that this is simply equal to GM R pi, which by definition is beta, but since beta is now being represented as a function of frequency, we should call that beta as the mid-band beta. That means we will represent this by beta 0, alright. GM R pi shall be represented as beta 0, and the other quantity I shall represent as j omega divided by omega beta, where obviously omega beta is equal to 1 over R pi C pi, alright, and F beta is omega beta divided by 2 pi. F beta is equal to omega beta divided by 2 pi. Can you now give a definition of F beta? F beta is the frequency. Well, if you measure beta from low frequencies to extremely high frequencies, then the the high frequency at which beta falls by 3 dB is the frequency F beta, and therefore F beta is known as the beta cutoff frequency. Alright, let me write this again. Beta omega as equal to beta 0 divided by 1 plus j omega by omega beta. Omega beta is equal to 1 by R pi C pi. The manufacturers do not measure C pi. What they measure in an automatic measurement setup, you see, they don't make one transistor a day, they make millions a day, and one cannot go on measuring a million transistors, beta and C pi and all this. So what they do is automatic. A transistor comes immediately, a machine, a robot hooks it up to a test instrument and it measures, it displays the beta versus frequency curve and it measures F beta, and this is the quantity that is specified. If you want for your design the given F beta, you can find out C pi from there because you know R pi. How do you know R pi? You know, pardon me? R pi is beta 0 by GM. How do you know GM? 40 IC. And beta 0 is specified by the manufacturers. They specify beta, they don't specify R pi, they do specify omega beta. Sometimes, most of the times, manufacturers specify, do not even specify omega beta, they specify a frequency called omega t. Omega t by definition is the frequency at which the magnitude of beta omega is equal to 1. Alright, magnitude of beta omega is equal to 1. What does it mean? It means that the current amplification just ceases beyond omega t. Isn't that right? If omega is greater than omega t, then beta omega will be less than 1, which means there is no current amplification factor. This is why omega t is called a transition frequency, transition from amplification to no amplification. And it is a matter of simple algebra to show from here, you put beta magnitude beta omega equal to 1 to show from here that omega t is nothing but beta 0 multiplied by F beta. Omega t is beta 0 F beta. It can be very easily shown from here. Maybe you will take this as a tutorial problem, or maybe you will set it in one of the examinations. Okay, it's very easy to show. Now, what does this mean? It means that even if F beta is not given, Ft is given, you can still calculate C pi. All this is directed towards C pi. And Ft has a physical significance that beyond this frequency the transistor is useless. Isn't that right? If it cannot amplify current, if I sub C is equal to I sub B, what use is such a transistor? So this is the absolute upper limit of frequency at which the transistor should be considered useful. You also notice that beta 0 has the dimension of gain, and F beta is the so-called bandwidth. Bandwidth, that is the band of frequencies within which the transistor beta remains to within 70.7% of its mid-band value. And therefore, this is a product of gain and bandwidth. And another name for omega t is GBW, gain bandwidth product. The Americans are very fond of many terms for the same quantity. They also call it the figure of merit of a transistor. That can be understood. If you have two transistors in which Ft is 1 megahertz and 10 megahertz, and you want to make a system at 5 megahertz, naturally you will choose the 10 megahertz one. That transistor is more meritorious than the 1 megahertz one. Alright, with this we conclude today.